the shear stress at point A is equal to Vy over Izz, right? 0.196 divided by 1. Now, this 1 is no need, I'm teaching now. That's why I put 1. And the thickness is equal to 0.2. Okay. Now, why this 1? Because down here is only what? Over there is only Q. Right? That's why this is a 1. If it's 2Q, you have to put 2. Okay. So 0.196 divided by 0.2 is equal to 0.98. Right? Vy over Izz. Okay. So that's what we got. Okay. So 0.98 at point A, right? At point B, which we found earlier, right? Oh, come on, move. Right? Which we found earlier is also equal to what? 0.98. Right? So I'm going to write over here. We also discover that at point B is also equal to 0.98 Vy over Izz. So the next point that we have to check, okay, is we have to check the centroid. Okay. So again, if you look at the question down here, okay, look at the question. Come on, Eugene. If you look at the question down here, right? They never ask us to check what? The stresses at the centroid. Right? But fundamentally, we know, right? There's a possibility, depending on the thickness, okay, that the maximum stress will occur at the what? Centroid. The question did not ask us to do it, by the way. You can see that, okay? But again, we have to check, okay, to see the ratio, right? Then we can determine our Vy over our Izz. Now, we know nothing, okay? So now, I'm going to analyze the stresses at the centroid, okay, two ways. By using the top and the bottom section, right? The Vy over Izz ratio at the centroid has to be the same. Okay, let me do this now. Okay, so we are going to let me elaborate. I need to show you. So I want you to be really comfortable. By the way, when I teach this course, okay, few years back, this is one topic that I'm so uncomfortable. Okay, it took me 2 times to teach to be comfortable, and now I can say that I'm really comfortable, and I've solved enough problems to make this topic easy. Okay, now watch this. Someone will say, yeah, right, Eugene, don't sound easy to me now, right? Wait, okay, give me time. So now we want to find the centroid. Okay, we want to find the stresses. Hey, by the way, thank you all for helping me solve that silly problem I had earlier. Okay, it's so annoying. Now I'm so relieved. Okay, so now we want to find point C. We want to find point C. Okay, so I'm covering. Okay, so we're going to find the shear stress at point C. Okay, so we're going to look at the top. Okay, so point C analysis from the top, and from the top we know it's box beam, right? It looks like a box, yes or no? And then you have what? 2Q. Okay, why 2Q? Because this is your Vy, right? And then you have one Q go one way, the other Q go the other way. So Q left, Q right. Okay. So now this is 2Q because it's linked at the terminal, right? So this is the terminal. Right? So it's split one left, one right. That's why you have the what? 2Q. Okay. So now we find our first moment of error. So Q at point C is equal to Q of the flange plus by Q of the web. Okay. Q of the flange. So I'm going to do what we have done before. So 2, the width is 2 minus 0.3 minus 0.3. And then the thickness is 0.2. And then this is equal to 1.5 minus by 0.2 divided by 2 plus, okay, the Q of the web. Okay, so the Q of the web, you have left and right. So this is 2. The width is 0.3. The depth is 1.5. And the Y bar is 1.5 divided by 2. Okay, so this will be equal to 1.5 minus 0.1 times 0.2 times by 1.4, 0.392 plus by 1.5 divided by 2 times 1.5 times 0.3 times 2 is equal to 0.675. So let me try again. 2 times by 0.3 times 1.5 times 1.5 divided by 2. Yep, plus by 0.392 is equal to 1.067. Okay, 1.067 inches to power Q3. Okay, right. So then immediately we can plug in our value. Shear stress at point C is equal to Vy over Izz. Qz is 1.067. Divide by 2 because you have left and right, and the thickness is equal to 0.3. Okay, I'm sorry, I should write for you guys thickness is equal to 0.3 because this is the thickness that we are concerned now. Okay, so 1.067 divided by 2 divided by 0.3 is equal to 1.778. So Vy over Izz is equal to 1.778. Okay, 1.7783. Okay. Now, so this one is analysis from, so analysis or top. All right, we analyze this from top, right, box beam analysis. Right. Now, I want you to be comfortable to be also able to use the bottom. Okay, you no need always use the top. So now if we were to do it from the bottom, okay, we're going to do from the bottom. So I'm going to copy this image. Okay. Then we're going to draw the centroid. Right. And then I'm going to, okay, so again we are trying to find what is going on at point C. Okay. So now we are going to use the bottom. So this is the top. This is the bottom. Okay, there's the top and there's the bottom. And then we have our Q. Okay. Our Q. Right. So this is Q on the left. This is Q on the right. They are not linked at all. Right. Right. Because at the bottom, so we are going to do shear stress at point C. We are going to carry out bottom analysis. And at the bottom, because the left is not linked to the right, right? So this is known as a wide flange analysis. Some of you might say, Eugene, why do I use the term the left is not linked to the right? Okay, so if you go back to this figure again, right? The left is not linked to the what? To the right, right? Whatever that is distributed down here, the left sees what the left sees, the right sees what, because they end up in separate terminal. That's it. That's why we call it a wide flange. Okay. Then from here, all right, wide flange analysis, right? So for this case, right, we know that we are going to look at Q only, and the thickness is still 0.3 inches. Okay, thickness is still 0.3 inches, right? So this is the area that we are concerned of. Okay, and I'm going to highlight again. Whether you take the analysis from the top or from the bottom, the answer has to be the what? The same, like what we did in our tutorial. Remember, right? You take from the top, take from the bottom, the answer has to be the same mathematically. Okay, it has to be the same. Right, so from the bottom, so we are going to look at the Q, okay, QZ, right? So Q of the flange plus by Q of the what? Web. Okay, so you don't need to go for left and right area. It's just one side. Okay, we just focus on the right side. So now the flange. Okay, so I'm going to take the width is 0.2, 0.7. The depth is 0.2, right? 1.5 minus by 0.2 divided by 2 plus by the web. Now the width of the web is equal to 0.3, right? The depth is 1.5 multiplied by 1.5 divided by 2. Okay, so this will be equal to 1.5 minus 0.1 times by 0.2 times by 0.7 is equal to 0.196 plus by 0.3 times 1.5 times 1.5 divided by 2, 0.3375. Right, so this will be equal to 0.196. 3375 is equal to 0.196 plus by 0.3375. So it's equal to 0.5335, okay, inches cubed. So therefore, the shear stress at point C is equal to V. V is equal to V is equal to what? Vy, we don't know, over Izz. QZ is 0.5335. And then divide by the thickness. Now the thickness is 0.3. Right? And this is only 1. Right? Why this is only 1? Because it's Q. It's not 2Q. Okay. So this will be equal to 0.5335 divided by 0.3 is equal to Vy over Izz, right? 1.7783. So this one we analyze from the bottom, right? Wide flange. And what you realize, if I zoom out a bit, what you realize now is whether you do from the top or from the bottom, when looking at a centroid, the answer has to be the same. Okay, this is one way to check whether you understand how you find first moment of area. Okay, this is the way to check. All right, so now the next thing is this. Okay, so now we found this. We found that any questions so far? Are you okay? Okay, I do apologize earlier. Okay, I'm so annoyed with the computer now. I cannot stop talking about it. So we know that stress at point A is equal to shear stress at point B. And this is equal to, so shear stress at point A equals shear stress is 0.98 Vy over Izz. Okay. And then we also know that shear stress at point C is equal to 1.7783 Vy over Izz, right? And we are given that the shear stress, the maximum shear stress is 10 times 10 to the power 3 psi. So you have equation 1 and then we have equation 2. So we know you cannot let equation 1 to be equal to tau max, yes or no? Because 0.98 is less than what? 1.7783. So with this, we know that shear stress at point C, right, is greater than shear stress at point A. Oh, you did write properly, sorry. So shear stress at point C is greater than shear stress at point A and shear stress at point where? At point B. So therefore, right, shear stress at point C will be equal to 10 times 10 to the power 3, and this will be equal to 1.7783 Vy over Izz. Right? Makes sense, yes or no? Right? So you have Vy over Izz is equal to 10 times 10 to the power 3 divided by 1.7783. Okay, so 10 to the power 3 divided by 1.7783 is equal to 5.623. Right, times 10 to the power 3. Okay, and if you have to put a unit in, this is equal to Newton per meter 4. Okay, right? So from here, right, remember what I told you guys, right? Vy over Izz is a constant regardless of the point you look at. So therefore, the shear stress at point A is equal to shear stress at point B. So this is equal to 0.98 multiplied by Vy over Izz. So this is equal to 0.98, right, multiplied by 5.623 times 10 to the power 3, right? So 0.98 623 power 3 is equal to 5510 or 5.510 times 10 to, sorry, I got my units wrong, okay? PSI. Wait, I'll change. So over here, this is pound force divided by inches to power 4. I do apologize. Okay. So we also know that the shear stress at point C is equal to 10 times 10 to the power 3 psi. Okay. So why I pick this example? Okay, this example shows you, right, what actually happened when it is a what? When it is a box beam analysis, right? And what it actually mean by a wide flange analysis. That's why I love to, in fact, this example is one of the most confusing example, but I like to pick this out because it shows you the difference in analysis between the wide flange and the box beam. Okay, so the next example is no more any easier. Okay, sorry, it's as confusing. But if I'm a good, if I understand the concept, okay, I can explain this really, really easy for you to understand. Okay, so that's where you know the person is an expert in the content. If he can explain something really complex and simplify it so that you can understand, right, easily, means the person is really, really good in the matter. Okay, I'm not saying I'm good yet. Okay, I'm saying that I can simplify it for you. Okay, so now let's look at another example. Okay, now this example is also very it is tricky but not impossible. Okay, it's just a structure that is confusing. Right. Okay, you look at this. Okay, so knowing that a given vertical shear cause a maximum shear of 75 times 10 to the power of 6 in the extrusion, okay, shown, determine the shear stresses at the 3 points: point C, point A, point B, and point C. So what is so unique about this problem is this, okay? So I'm going to tell you why this is unique. It combines, okay, both thick wall, thick and thin wall analysis. Okay, so this is one of the problem that they combine thick and thin wall, and you need to know when to use what thickness. Yes, right. You need to know when. Okay, if you don't know when, you are done. Okay, so the first thing, as usual, we are going to construct our shear flow. Okay, we're going to construct shear flow. So this is our Vy. Right, and then one will go one side. The control is the web, so the web is coming down this way. And then it does this. Okay, so what I propose now, okay, is we go for a break. Okay, we come back at 8:40. Okay, we go for a break. We come back at 8:40. Okay, thank you.